Swayam Prabha. Digital India. Educated India.
Welcome back, students. In this lecture, we will talk about OPAMP non-idealities. In the first or second lecture, when we talked about the OPAMP, we looked at ideal operational amplifier, and I described the characteristics of the ideal OPAMP in terms of gain, input impedance, input resistance, output resistance, and things like that. In reality, the OPAMP is made using devices, actual physical devices, and these devices have their own shortcomings. Due to that, you have some non-idealities which creep into each op-amp. Two of those non-idealities we are going to talk in this lecture. One of them is DC offset voltage, and the second one is DC offset current and DC input current. And they happen because of certain types of devices, for example, BJTs or MOSFETs being used inside the operational amplifier. So let's discuss in detail. So the first non-ideality we're going to discuss is DC offsets. Now, as I said, each operational amplifier is made using devices. Let's kind of physically draw those devices to see. So, for example, in this particular example, I'm going to show you that there are some MOSFETs at the input. Now, since initial assumption is the op-amp is ideal, when we say the op-amp is ideal, we are assuming that the devices which are at the input, they are exactly same, meaning both these devices, let's say in this case, let's call them M1 and M2, they are identical. In reality, when we manufacture the op-amps, the devices can be slightly different from each other, and that results in an input offset voltage, which I'm going to describe it to you. So let's say this is your plus and minus terminal. So the input, the DC offset, we model it as following. So we show the ideal op-amp plus minus, and then we say that here is a small amount of DC offset which we show at the input. In this particular case, I'm just showing this offset voltage, which could be as small as could be microvolts, millivolts, or tens of millivolts, depending upon the types of devices which are used. So we insert this offset voltage at the input of the op-amp, which will quantify the mismatch between the two inputs. Okay, and this is your ideal op-amp. All right, and this is plus and minus terminal. Now the sign of the offset voltage is not really important, because it could change from let's say we manufactured 100 op-amps, let's say, using any process, foundry process. Now each version or each implementation or each chip, the mismatch between the input device M1 and M2 is going to be different. Okay, so we take one chip, we find that VOS is equal to plus 5 millivolts. The second chip is let's say VOS2 is equal to plus 3 millivolts. The third chip could be 0 millivolts, very close to each other, and the fourth chip could be minus 3 millivolts, something like that. So this is a statistical property of the devices, matching between the two devices. Okay, so the polarity, as I said, it's unknown. And now what does this offset voltage really do to the op-amp? So let's assume for a minute that the input referred offset voltage is, let's say, 10 millivolts. Okay, so we are going to draw this op-amp, and we can say that this is plus minus 10 millivolts. Okay, now let's assume for a minute that this ideal op-amp has a gain of 1000. All right, now if I short the two inputs and connect them to the analog ground like this, what do we expect to see at the output? So you will quickly realize that this positive terminal is connected to the negative potential compared to the negative terminal. So we expect the output voltage to drop. Now you would say that, hey, this is 10 millivolts and this is gain of 1000, so I should see something like a minus 10 volts coming at the output. However, if the op-amp supply voltage is, let's say, 0 to 5 volts, then this cannot happen, right? You cannot get minus 10 volts, so you would end up getting 0 volts at the output, because the output of the op-amp will get saturated to the lowest potential. So this is an important fact you should understand in terms of concepts. Okay. Now let's draw transfer characteristics of the op-amp. So let's say if we have an ideal op-amp, and I'm only plotting, note the scale here. So this is your output voltage and this is your VID, which is in millivolts, and output voltage is in volts. All right. So if the op-amp is ideal, then we would get the characteristics. Let's say this is 5 volts and let's say this is 0 volts. The characteristics would look like this, something like this, and the slope of this curve would be 1000, because AV is 1000. All right, and this would be 0, something like that. Now if we have an offset of 10 millivolts, which is shown, let me use a different color and use a green. So if the VOS is equal to plus 10 millivolts, all right, which means I have to apply an input voltage. Let me draw a separate picture for you so that it's easy to understand. This is VOS plus minus, and now this becomes our new op-amp right here. We can create this model of the op-amp using which has the offset voltage built in as such, like this. Okay, so this becomes our V out, and this becomes our positive input, and this becomes our negative input. Now if I apply VID between these two, what is the transfer characteristics? So if VOS is equal to 0, then we know it looks like the ideal characteristics of the op-amp, as I have shown already in the picture here. Let's say VOS is 10 millivolts with the sign as I have shown here. Let's say 10 millivolts over here. Then I would like you to think about is what would be the direction? How would the transfer characteristics move? Would it move up or down, or would it move left or right? I want to give you 10 seconds to think about it. Okay, so you can see that I need to have plus minus 10 millivolts here to have a net 0 input at the input of the op-amp. So with this kind of sign, we would expect the transfer characteristics to move to the right. Okay, and the transfer characteristics would look like this, something like this. The entire transfer characteristics would move to 10 millivolts here, like this. And if the VOS was minus 10 millivolts, then we would see the transfer characteristics which would look like this, something like this, and this would be your minus 10 millivolts. Okay, let me redraw this so it looks something like this, and this would be minus 10 millivolts when VOS is minus 10 millivolts. For circuit analysis, you can model this VOS voltage source on the positive or negative terminal according to your convenience, and we will see what I mean by that convenience. And then we can generally whenever you have multiple input sources, it could be offset voltage, it could be input voltage 1 or input voltage 2, then you should try to use superposition theorem to make your life easier. So we can study the impact of offset voltages using by zeroing out the input, and then we can use superposition. So for ease of analysis, I like to keep offset voltage on the wherever there is no feedback. Okay, it behaves exactly the same way. It's just that analyzing the circuit becomes very easy. So let's take a couple of examples, and this point will be clear. So let's take a simple example, which is, we call it unity gain buffer. So if this is V in, then we expect, because of virtual short between these two, we expect V out is equal to V in. In this particular case, we are assuming gain is very large. Okay. Now, if we have offset voltage in this op-amp, then the situation will change slightly. So what we would do then is we would erase this, let's say. Let's erase only this portion right here. And then, as I said, we would introduce offset voltage in the non-feedback terminal. So this would be plus minus VOS. So you can immediately convince yourself the input voltage over here using Kirchhoff's voltage law will be V in minus VOS. Hence, the output voltage will be also V in minus VOS. As I said again, the sign of the offset voltage is not important, because from one part to another part it will be changing randomly, right? So offset voltage can be positive or negative. So you have to keep that in mind. The next example I'm going to give you is your conventional inverting amplifier. So in this case, we know V in, this is R1 and R2. So V out will be equal to minus R2 divided by R1 times V in. And if we apply the offset voltage, let's say we apply the offset voltage as follows, plus minus VOS. Now what do we do? To figure out, as I said earlier, we will use superposition theorem. To apply the superposition theorem, we would first ignore this input, we will ground this out, and then we would apply VOS. In that case, this potential will be VOS, and it looks like a, from this point, it looks like a non-inverting amplifier. And you can quickly convince yourself the output would be 1 plus R2 divided by R1 times VOS. Okay, so this was your ideal situation, and this is an extra term which will come in, that would be an artifact due to the offset voltage. As I said again, the sign of the offset voltage is not important. The sign of the offset voltage will change from one chip to another chip. Okay, all right. Now the true impact of the offset voltage you can really see using a numerical example. So let's take a numerical example which will make you comfortable. So here what we're going to talk about is a cascaded amplifier stage. Please draw the schematics in your book so that you become comfortable with different op-amp configurations. Here is the first amplifier. Okay, so here is my first input V in, that's applied. This is R2, R1. Remember, feedback should be on the negative terminal. And then this is going to give me some gain, but it's not enough for me, so I'm going to add another stage here. So the next stage is going to be looking like this, minus plus, and here is your next amplifier. Here we call it R4 and R3. Okay, first of all, let's see what the output will be just due to the input voltage. Okay, so the output due to input voltage, as we can see, VO1 here and V out. So VO1 will be, I'm sure you have figured it out already, R2 divided by R1 times V in. And this gets multiplied again by 1 plus R4 divided by R3. and that will be equal to your V out. Okay, so that's the overall gain that we are trying to get. So let's say if this was 99, R2 divided by R1, and let's say R4 divided by R3 is also 99, then we get V out is equal to 10,000 times V in. Got it? Now, this is the ideal scenario. Now let's analyze the impact of offset voltage. So we can quickly see that let's insert offset voltage. As I said, we would like to insert the offset voltage, input referred offset voltage of the op-amp. Let's call this amplifier A1 and this is op-amp A2. Now, key thing to note is each amplifier will have its own offset voltage, but offset voltage of each amplifier will not be same even on the same chip because they are made with different devices. So amplifier A1 may have VOS1, amplifier A2 will have VOS2, something like that. And they could be positive, negative, depending upon the devices which are actually used to implement those amplifiers. All right. So we can now analyze the effect of, analyze the effect of VOS1. For that, what we will do is we will remove the input and we will insert the offset voltage here. So this is our offset voltage plus minus VOS1, and at that point we will ground the input. So you can quickly see that the contribution of offset voltage is going to be, and let's insert VOS2 also, and that I'm going to introduce here something like this. V out will be equal to VOS1, and this again is a non-inverting terminal, so R2 divided by R1, and that will get multiplied by another 1 plus R4 divided by R3. This is due to VOS1, and due to VOS2 we can see it will be plus VOS2 1 plus R4 divided by R3. Okay, so now we can add these three terms together, and then you can see that the equation will look like this. V out is equal to V in plus VOS1 1 plus R2 divided by R1 plus VOS2 and multiply by 1 plus R4 divided by R3. Just math. Okay. And as I said again, if this is 100 and if this is 100, then we can quickly see the V out will be equal to 10 to the power 4 times V in plus 10 to the power 4 times VOS1 plus 100 times VOS2. Okay. So let's say the VOS1 is 10 millivolts, then this contribution would be equal to almost 100 volts. Okay, so the amplifier would rail out, as we like to call it. It will get clipped one way or the other, and this part will be equal to 100 times VOS2, which is let's say if it was 10 millivolts, and it could be some random direction, it could be plus minus whatever. So we are only going to look at the kind of magnitude, not the sign of the contribution due to offset voltage. So in this particular case it would be 10 millivolts multiplied by 100, which is 1 volt. Okay, so the quick thing to note here is that let's say you have a series of amplifiers, just like what we have done here, cascaded amplifiers, then the offset of the first stage dominates because it goes through a lot more gain. Okay, so in this particular case the offset VOS1 will dominate the output. So you have to be aware of impact of offset voltage, and so when you buy an op-amp, just like the example I gave you earlier, how do we get rid of this offset, first of all? So what you can do is there is something called trimming of the amplifier. So this offset can be trimmed manually, and each manufacturer will provide you some circuit which is telling you that, hey, you go in there and you put a trim pot and you zero out each amplifier's offset. You can do that, okay? But that's a manual process. The second thing, as designers, what we like to do is we like to use capacitors to our advantage. So if you use a capacitor, and we like to call that DC blocking cap. So if you use a DC blocking capacitor, then the DC offset from each amplifier will not propagate further. Okay. So for example, let's take an example. Let's say this is one amplifier, this is second amplifier, and if I insert a capacitor in between, then as far as DC is concerned, the signal DC will not go through. Okay, only AC signal can go through. So I'm giving you really elementary or rudimentary explanation, and all this stuff we're going to go through in detail as we dig into the devices. Okay, but just the concept is the capacitor does not allow DC to go through. The important caveat here is that your signal content, should not contain DC, because otherwise the signal will also get blocked. So let's say you're talking about voice signal, which is from 20 hertz to 20 kilohertz. Okay, then you can use the capacitor as a block. As long as everything in this frequency range is moving forward from one amplifier to another amplifier, we are okay. We just don't want the DC from one stage to get amplified and saturate the next stage. So this is one issue that you have to deal with as we design complex circuits. Okay, the third solution is an offset cancellation circuit techniques. So these are very popular. Here what you do is you go through some kind of offset cancellation cycle. Okay, so for example, you have one amplifier, and then you store the offset in the calibration cycle on VOS prime over here. And in the next phase, what you can do is you can use that capacitor and subtract out the VOS as we go along to the next stage. So this required some kind of special timing provisions, because you need to go through a cycle for offset cancellation techniques sometimes. Okay, so these are various techniques that people use to cancel out the offset. This comes into play mainly in case of amplifiers which are using BJT transistors. Okay, BJT transistors have small amount of input current flowing in them. So MOSFET transistors have a gate. Okay, so there is the amount of current flowing in this gate is virtually zero. However, the bipolar transistors generally have a base current. Okay, and that base current is going to be fraction of what the collector current is. All this stuff I'm going to go through in upcoming lectures, but at this high level discussion, you should just assume some current is flowing inside the amplifier. So what we can do is we can show the DC bias current flowing in the amplifier like this. So there will be some current flowing this way, and there will be another current flowing this way. Okay, so this would be a positive input and this would be a negative input, and let's say there is IB1 and IB2. Okay, and this is your VM. Now one thing I would like you to remember, if you remember, there is a whenever we have let's say V1 and V2 applied to positive and negative input, then we are quick to come out with two properties, which is VCM, which is equal to V1 plus V2 divided by 2 and VD, which is differential voltage, which is V1 minus V2. Okay. Similarly here, we can also come up with average input current, input bias current into the amplifier, that we can call it IB1 plus IB2 divided by 2. Okay. And the difference current, we like to call it input offset current, and that we can say it's mod of IB1 minus IB2. The reason we use mod is we don't know, due to manufacturing variation, is IB1 greater than IB2 or the other way around. So we just like to show difference between them without any sign as a mod. Okay. So for example, if you look at the bipolar transistors, okay, IB1 and IB2 each can be of the order of let's say 100 nanoamps, the base current, and then the offset voltage can be of the order of, I'm sorry, I made a mistake. This could be of the order of 100 nanoamp, and this could be order of 10 times less offset current. Okay. So we can analyze the impact of these bias currents as well as the offset currents using circuit examples, and then it will become clear to you. And I'll show a technique which we can use to mitigate this offset current. So let's take first example, our favorite non-inverting amplifier, R1, R2, and here is the current flowing, IB1, IB2. Okay, the current is flowing in this direction. Again, this is just a notation. And we are applying a input voltage at this point. So how do we analyze this circuit? So let's analyze the effect of IB1 and IB2 separately. So in that case, we will assume that the input voltage is 0. We know what input voltage does at the output, and now we are going to try to figure out what the output due to just this input voltage is going to be. 1 plus R2 divided by R1 times Vin. And we want to figure out what is the transfer function of IB1 to the output and IB2 to the output. Okay. So let's, we can redraw this schematic a little bit better as follows. And here I'm just grounding the input. And here we have IB1, and here is our IB2. This is minus and this is plus. So I have removed input voltage and I have only put in IB1 and IB2, and we're going to see what happens at the output. Okay. Now if you look at IB2, it's flowing between one analog ground to another analog ground. Okay. So IB2 really doesn't have any impact on the output. Okay. So convince yourself, IB2 is just a current flowing between one analog ground to another analog ground, and it doesn't develop any voltage at the positive terminal. If we look at IB1, again, what is the voltage at this point, at the negative terminal of the op-amp? Since the gain of the amplifier, AV, is very large, we know that it's a virtual short. The negative and positive terminal are a virtual short, as a result of which the negative terminal will also look like analog ground. It will look like an analog ground. So there will not be any current flowing through resistor R1. So all the current IB1 has to flow through our resistor R2. Okay, so you can quickly see then the voltage at output due to the bias currents is going to be only due to IB1, and that will be equal to IB1 times R2. Okay. So we can modify our output equation to include the effect of IB1 R2, and this would be your V out. So it would have a V in component which is desired, and this would be your undesired component. Okay. So what's the problem with this one? The problem is we want to get high gain with this amplifier. So we typically try to increase R2 as much as possible to get high gain, because we want ratio of R2 divided by R1 to be large. As soon as you start increasing R2, this component, which is IB1 times R2, will start coming into play. So this requires that keep R2 small, and that kind of limits your gain that you're going to have. Okay, so don't lose heart. There is a way we can mitigate this effect, and very simple solution which I'm going to show you. Let's see. So this is your original amplifier, R1, R2, and we are going to add another resistor here, minus plus, and that would be my V in. And this resistor, let's say, is call it R3. Now, as far as the signal path goes, the AC signal path, this R3 doesn't do anything. Okay, and I'm going to draw, this is IB1, this is IB2 in this direction. Okay. Now one thing to remember is IB1 and IB2 will have same direction because they represent the base current of the amplifier. Okay, depending upon PNP or NPN, you will have same device on both sides. It's just that their value will not be identical. Okay, so we can, that's why I'm showing them in the same direction over here. So you can quickly prove for yourself that just due to the V out due to V in is identical, 1 plus R2 divided by R1 times V in, and the V out contribution at the V out contribution due to IB1 is going to be the same, which is plus, this is the IB1 times R2 contribution, so this would be same as before, IB1 times R2. And when we look at IB2 only, transfer function for IB2 to output, what you would do is you would remove the input voltage, you would remove IB1, and you will see that this IB2 current has to flow here in this particular resistor, and this voltage is going to be minus R3 times IB2 at the positive terminal. So from the positive terminal to the output, you will have 1 plus R2 divided by R1, okay, and then you have R3 times IB2, and that has a negative sign. So we can, you can then see that if you want to mitigate the effect of IB1 and IB2, you would like these two gains to be approximately same. In that case, what will happen is if we choose R2 is equal to 1 plus R2 divided by R1 times R3, if we do this, okay, which in a way is telling you that R3 is equal to R1 R2 divided by R1 plus R2, which is R1 parallel R2. So if we meet this condition, then our V output voltage becomes, it will become 1 plus R2 divided by R1 times V input, this is the desired term, along with that you will get R2 times IB1 minus IB2, that is your I offset. Okay, do not confuse this with iPhone operating system. This is offset current. Now what have we gained by doing this? What we have gained is IB1 and IB2 individually, they are generally large numbers, but the difference between them can be an order of magnitude smaller. So by simply adding this resistor, we are able to reduce the impact of offset currents to difference between the offset current. Okay, so this is the way to reduce the impact of bias current, input bias current.